Venus. It's one of the most hellacious environments in our solar system. And if you're going to try and put something on the surface of Venus, you need to first survive a 100 G load upon entering the atmosphere. Next, you have to descend through a sulfuric acid atmosphere that'll eat away at metal, and then descend through 90 times Earth's pressure, with a pressure so intense that it'll crush the hull of a nuclear submarine. And the Russians tried repeatedly to put a lander on Venus, and after many tries, finally in 1970, they succeeded in their first lander, but ran into the final problem, the surface temperature of 460 Celsius. The mission was only designed to last for 2 hours before the electrical systems succumbed to the high temperature. Now, modern mission proposals don't improve on that very much more. They have added a lot of complex systems to try and keep things cool, but still can't extend the life beyond 24 hours. Now, that creates a problem. First, you have a hard time convincing a government agency to fund you when you're just proposing a 2-hour mission. Secondly, there's a lot of interesting effects on Venus, and to understand the planet, we can't do it in just 2 hours time snippets. We need to be there for days to understand how weather and different patterns occur on Venus. So at JPL, we started to look for another solution, an idea that could have us operate on the surface of Venus for not just days, but for months. Oh, and instead of just landing and being stationary, we could rove. And we found this solution in mechanical computing. Now, of course, designed with the right high temperature alloys, we can operate at those Venus temperatures. Mechanical computers were developed in the 1940s and 50s, a lot in World War II. Here you can see an example of a differential adder. You have 2 inputs here, x1 and x2, and then get a third output here, x3, which is the sum of those 2 added inputs. You have a mechanical multiplier here, where you can see the various linkages are multiplying 2 and 3 to produce 6. And then, of course, there's mechanical equivalents for differentiation, integration, so on and so forth. So we started looking at implementing this for a Venus rover in the traditional rover architecture. And one of the problems we ran into as we started to pull together all these mechanical computing elements to start doing the computations necessary to operate a rover is it got really heavy really fast, and friction became a problem, and just slowed the system down to a halt. So we had to look to somewhere else for inspiration. And the Strandbeests is where we got that. The Strandbeests are these amazing creatures created by Dutch artist Theo Jansen. And what's really amazing about this is the logic that's built into them. They're very simple reactive sensors that basically respond to the environment that they're in, and they'll sense as they start to walk into the water or as they start to walk over soft sand, and just simple sensors that flip a single switch, cause the legs to swap to change the other direction, and walk away from danger. So we started looking at that in the Venus context and came up with something like this. A device powered by the wind, walking across Venus. It could place instruments and then communicate with an overhead satellite using a radar target retroreflector. And as we started developing this concept in the first few months, we had a A-team study, which is an architecture team at JPL. And we actually had Theo come over from the Netherlands to help give us some pointers on what would he do if he was doing a Strandbeest on Venus. And one of the first things he told us is eliminate the legs. They work on the beaches of the Netherlands, but once you get to soft sand, or especially if you get into rocks on Venus, they're going to be unstable, trip you up, and you're not going to have a stable rover. So we moved to something that looks much more like a tank. Well, it was actually inspired by a tank, World War I tanks, which were designed to cross trenches and operate in extremely difficult and hazardous environments. We've moved the wind turbine to the center of the rover such that we can flip over and roll and still continue to drive forward. So we've designed it so it's a very robust rover, and then we can use obstacle avoidance when needed to get away from obstacles that are problematic. And this shows what sort of the overall system looks like. We basically input wind power. We have a distributed computing system which responds to the various hazards that we may run into or see as we're crossing the Venus environment. But I wanted to come back and talk a little bit about what was sort of the core innovation in this that enabled us to move forward. And really the first thing we were trying to do is initially we were going at this with a traditional centralized model where you have one central computational node which takes in a bunch of inputs and then makes a decision from that, much like you have on the current MER and Mars Curiosity rovers. But that didn't work for our mechanical computing, as I said earlier. So instead, to enable this, we had to move to a distributed model, which has many simple rules leading to a complex behavior, basically many simple decisions leading to a complex emergent behavior. So one of the things we realized is we had to decrease the complexity of the entire system as a whole and instead make it a very small reactive system to be able to enable something that can operate on the surface of Venus. So there's a number of individuals I'd like to thank here. The ones in bold are the folks on the team, but there's a lot of great individuals that have given me pointers on this idea. It's absolutely magnificent how many people have ideas to share with you on how to implement this concept. I'd also like to thank our funding agency, NASA NIAC, NASA Innovative Advanced Concepts. And if any of you have ideas for how to implement a mechanical rover on Venus, I'd love to hear from you. Thank you.